Hello and welcome to this AI coffee break. Recently we have seen how transformers are being applied not only on text but on images or even on both combined. How is this possible? Aren't images and text so different? We read text from left to right and images are something that we perceive at once. Or do we? In this video, we will explain why images and text can be similar in the eyes of a transformer neural network and point out what really makes images and text different. Difference that could make the transformer stumble. On the representation level, what is text? Text is a sequence of characters or words, and it's a sequence because we read from left to right in English. But neural networks do not work directly with characters nor with text. Neural networks work with points determined by coordinates or numbers in high-dimensional spaces. Neural networks are great at squeezing, stretching, and bending the input space so that the similar data points get close together and are easy to discriminate from dissimilar data points. So the transformers working with numbers request that characters or words are encoded into vectors. These vectors are ordered, preserving the sequence structure of the text. There are neural architectures like the LSTM, where this order is captured intrinsically by the architecture. The LSTM looks at every word vector one after the other. But the transformer works on sets, looks at everything in parallel, so for the transformer to know this order, positional embeddings are added to the vectors. The vectors can be initialized with numbers where words belonging together are already together, or they can be one-hot encodings or token identifiers. It is always up to the loss-constrained neural network to figure out a better inner representations where words belonging together are shifted closer to each other. And that was it for text. The rest is transformer magic. Check out our video explaining how the transformer works, linked below. Then what are images? Grayscale images are a matrix of numbers. A high number corresponds to a high light intensity in that region. A low number is a darker spot. For color images, we just have a stack of 3 of these matrices, each corresponding to the red, blue, and green channel. A high number in the red matrix corresponds to a high intensity of red light. But once the image is stored, the computer has these 3 matrices and the color is not exactly there anymore. The computer would not notice if we would just exchange the numbers between these matrices. Color occurs again in your monitor. If there is a high value in the matrix labeled with red, it will emit light with the certain light frequency that we call red. So let's look at the word vectors again. If we take their sequence and put them one under the other, we have an image. Crazy, right? Let's undo this and do something different instead. Take the image and treat it like a sequence of rows. And this idea is not even that crazy. It is exactly how cathode ray tube screens in old TVs and old monitors treated this matrix as a sequence by drawing the image from left to right and from top to bottom. In this way, the representation of text and images is the same. The text is a sequence of word vectors, the image is a sequence of image vectors. We can add positional embeddings and the transformer is ready to process text or images individually, or both at the same time for multimodal integration. And the transformer can process them quite efficiently because computations are in parallel on this set of vectors, which is not really a sequence, it's a set. The sequentiality is quite artificially encoded in these positional embeddings. In this way, the transformers kind of butcher the way we humans thought about text and images. We are comfortable with the LSTM's inductive bias of looking at one word after the other. So why is the transformer looking at everything at the same time? Well, I do not know about you, but for me, when I'm reading out loud, I have to peek much further away into the sequence to get the right intonation. I also peek into the past by short-term memorization, which is honestly better than the memory of the LSTM. We are also comfortable with CNNs that do a very similar kind of processing as what happens in our eyes. But applying these kind of biological inspiration on neural networks and restricting their solution space with biases is also unfair to them. It is important to take as much inspiration from the biological optimization algorithm, especially when it comes to energy efficiency, but we should also look beyond, like with the transformer that is free of the LSTM and CNN inductive biases. Okay, so we have seen that images and text can be represented the same, and the transformer heavily takes advantage of this, but if images and text are represented equally, does that make them equal? Well, no. Images and text are not born equal. Therefore, they become very different content-wise. Vision is often an evolutionary necessity and evolved independently in many species. Language, human stroke of genius, came later after humans already had their vision. Being invented, it is based upon many agreed upon rules. Therefore, text is in a way already compressed. It omits a lot of stuff. We do not say that the grass is green if it is a visual common knowledge. Also, in the datasets transformers are usually trained on, there is little if no figurative speech, and there are very few ways to say, for example, cat in English language. In contrast, images of cats can look very, very different from each angle, camera setting, and so on. So, omission of the visual information in language, the necessary and somewhat arbitrary rules of language, cultures, and languages are few of the many things that make text and images quite different in content. There is overlap, but they are also complementary. And Miss Coffee Bean thinks that this is so exciting that the representations and the processing is similar, but the content and nature of text and images are so different. When the transformer acts on language, we sometimes do not see the language phenomena because of so much transformer complexity. And the other times we do not see the transformer because of so much language. So it's more than helpful to learn something about transformers, text and images by seeing them interact in different constellations. It's more or less like a complicated ablation study, and the takeaway for multimodal integration of all these three together is that even if text and images are represented the same, they are not equal in their content, giving transformer models a hard time to integrate them. The tendency is to kind of ignore the visual information and rely on the text because text is already so compressed and its biases are more easy to be picked up. To find out more about this vision and language inequality and its effects on multimodal learning, check out our video about this link below. In any case, Miss Coffee Bean gets out of here now. Right? Hey, Miss Coffee Bean. Miss Coffee Bean. Miss Coffee Bean, come.